So let's start diving into different ways we can improve our models using hyperparameter tuning. The first one here is by hand. So let's make a little heading. 5.1, tuning hyperparameters by hand. And so far, we've talked about dealing with training and test data sets. A model gets trained on the training set, it finds patterns, and then it gets evaluated on the test set, so it uses those patterns. But hyperparameter tuning introduces a third set, a validation set. So if we have a look here, this is what it's going to look like when we tune hyperparameters by hand. So if we were starting with 100 patient records in the case of our heart disease problem, and now again, this may change depending on what problem you're working with, and I've just used the number of 100 because it's an easy number to picture. So this is our starting data. And what we might do is split it. This is what I mean by 3 different sets. So we split. We might use 70 to 80%, so 70 patient records as a training split. We might use 10 to 15% as a validation split. And we might use 10 to 15% on a test split. Now, of course, you can adjust these numbers. These are just some common numbers you'll see used. And so, naturally, the model gets trained on these, is what we've seen before. And usually, without the validation set, our model will get evaluated on these. But now, because we have a validation set, this is where we're going to tune our model settings, aka the hyperparameters get tuned on the validation split. And then, finally, as normal, a model gets evaluated on the test split. And now the analogy here is, if you remember right back at the start, it's the most important concept in machine learning is the 3 sets. So this was right back in the start, Machine Learning 101. The training set is analogous to, say, you were at a university course and you were learning the course materials. The validation set is where you would test your knowledge a little bit and see what you need to adjust. So you would get the practice exam from your professor, and you try it out and you go, oh wow, I'm doing terribly at questions 1, 2, and 4. Maybe I need to adjust the way I approach this. And then you do the practice exam again. And once you'd improved your skills on the practice exam, you'd feel a little bit confident and you'd finally really evaluate yourself on the final exam, which is the test set. So how would we do this with code? Let's come back to our notebook. Tuning hyperparameters with hand. Let's make 3 sets. Training, validation, and test. So what we'll do is we'll just remind ourselves of our get params. We'll remind ourselves of our random forest classifier's baseline parameters. So these are all the baseline parameters, aka the settings on our model which we can adjust. And now, in fact, which ones are we going to adjust? Well, after reading the random forest documentation, and again, you can do this for any machine learning estimator or model with Scikit-learn, we start to get an idea of how we could adjust each setting. And even with some of the models, there'll be some notes on different hyperparameters Scikit-learn suggests to change. That is kind of like the ones you want to change first to try. And so after reading through that, after going through that, so in our case, we're going to try and adjust the following. So we want max depth. Actually, we'll put these in backticks because we know that they're code. Max depth, max features, min samples leaf. If none of these make sense, remember the definition to all of these is in the documentation for any model. So if we come up here, min samples leaf. The minimum number of samples required to be at a leaf node. And you can read more in depth in what a leaf node is if you check out some resources on a random forest in depth. But for now, we're just focusing on how we can adjust hyperparameters of a machine learning model. Min samples leaf, and min samples split, and n estimators. Wonderful. So these are the hyperparameters we're going to adjust. And now we'll use our same code as before, except this time we need to create a training, validation, and test split. We'll just use these splits here. So the training split will create with 70% of the data. The validation and test sets will each contain 15. And we'll get some baseline results. So we've kind of already got them, but we'll do it again, get some baseline results. And then we'll see how we can tune the model's hyperparameters by hand. And since we're going to be evaluating a few models, I think it's important that we create an evaluation function. So this is what you might want to do, whatever model you're working on, is create functions if you know you want to do something more than once. So it saves out writing lots of code. But again, that's probably a bit different to what we've seen in the past, right? We know we like to write everything out by hand. We'll just leave a little doc string here. Performs evaluation comparison on Y true labels versus Y pred labels. And now, as we saw in the evaluation section, the main thing evaluating machine learning model does is it compares its predictions versus the true labels. So that's what this function is going to do. So because we're working with a classifier, we want accuracy, accuracy score, Y true, Y preds. We also want precision. And now we might actually note here on our classification model, because if we use this evaluate preds on a regression model, we're putting in classification metrics, we're going to get errors because a regression model predicts different things to what a classification model predicts. Precision, and then we want recall, of course, equals recall score. And now again, you could adjust this evaluate preds function for what you need, but I'm just going to include some of the most common metrics that we've covered for the classification models, some of the things you want to pay attention to for basically all of your classification models. Y preds, and then we'll create a dictionary so it can return the predictions so we can compare them with other predictions later. Round, accuracy, we'll go to 2 decimal places. Yep. Precision, round, precision, 2. Now always remember, if this seems like a lot, it's because, first of all, it kind of is a lot to take in one hit. And the second thing is that I've had a fair bit of practice with this. So I inherently know what to use. Again, I'm always learning, but I've just had a bit of practice building these specific kinds of systems, and these patterns come up time and time again. We go print. We want, just to give us a little bit of printout of what's going on, we'll go accuracy times 100, and then we only want 2 decimal places. That will be enough. Then we'll go the same thing. Go F, precision. This can be precision. We won't need to times that by 100. That can just stay at 2 decimal places. Oh, we need a string ender. Wonderful. Print. Then we're going to go recall. This is a lot to type out to begin with, but because we'll be able to reuse it, it's going to save us down the track. And then finally, we want print F1 score. We're making it. We're finally making it. Excellent effort. There we go. Okay. Oh, and finally, we want to return our metric dict. Now, what is happening here? Well, essentially, this function just takes some true labels and some prediction labels from our classification models. We know this from the string here. It's going to compute different evaluation functions here, and then it's going to return a metric dictionary so we can save that for later. And it'll also print out some metrics so we get a printout as soon as we run this function. So it's just an evaluation function for our classification models. Wonderful. And I'm going to save the notebook here as always. And now, how exactly would we create these train, validation, and test splits? Well, our train test split function that we've seen before, remember this one? Train test split. So this one only returns train, splits arrays or matrices into random train and test subsets. So this one only splits into train and test sets. So what we'll need to do is we'll need to manually split our data into train, validation, and test sets. And so to do this, we can, how can we do this? Because our data is in a data frame, heart disease, we should just be able to do it using some good old math and indexing. Let's see how we would. So from Scikit-learn, we'll import our model first, even though we've already instantiated a random forest classifier. Let's go np random seed, and then we'll shuffle the data. Why are we shuffling the data here? If we're splitting into train, validation, and test split, we want to mix it up. Make sure it's not just the same the records are coming in the order that they come in. If we're using slicing to create our train, validation, and test split, we want to make sure all of these records are jumbled up. So that's what we'll do. We can shuffle it using pandas sample function. We'll do frac equals 1 for 100% of the data. This is just going to take the heart disease, sample it, this is randomly, and then reassign the heart disease data frame to its normal variable. So it'll just take this, sample a bunch of rows at random, and then reassign it to this variable, aka shuffling the data. Now the data's been shuffled, we'll split into X and Y. Actually, we might save that to heart disease shuffled. That's a better idea. X equals, this time we need heart disease shuffled, and then we're going to drop the target column here. This video is dragging a little bit on, but this is an important concept, right? We're going to see here, it'll all be worth it because we'll be able to improve our models using hyperparameter tuning. Split the data, validation, and test sets, wonderful. So the train split, how are we going to do this? Well, we need to create a number that we can use for slicing. So we want 70% of the length of our data. So you see what's happening here? Train split, we need a number. We need 70%, so 0.7 times the length of heart disease shuffled. And this is going to be 70% of data. And then we need a valid split, which is going to be, do you remember? Do you remember what the split is? 15%, that's what we've agreed on. Wonderful, so we can do that in the same way. That will be train split. Because we want to index, we want the next 15%. So train split plus 0.15, the length of our heart disease shuffled data frame. This is 15% of data. Wonderful. And so X train, Y train is going to be the X data up to the train split, and the Y data up to the train split. Wonderful. And then X valid, Y valid, sorry, is going to be the X data from the train split to the valid split. And the same thing for Y is going to be the Y data from the train split to the valid split. And then we're going to have X test is going to be, and Y test is going to be the X data from the valid split onwards. So the rest of the data. And then Y from the valid split onwards. Whew! That was a lot so far. Let's just see what's going on, right? Let's go len, print it out, X train, and then we want len X valid, and then we want len X test. Okay. So the training set has 70% of the data, aka 212 rows. The validation set has 46 rows, 15% of the data. And the test set has 46 rows, so that's 15% of the data. There's different amounts here, even though they're both 15%, because we've used round. We have an odd number of samples in the heart disease shuffled data set, so there's going to be a spillover of 1 somewhere. That is perfectly fine. Okay, now we have our splits. We can do CLF. We'll instantiate a random forest classifier. And now, because we've passed nothing here, this is going to instantiate it with the baseline parameters. So if we do this, clf.getParams. Oh, that's not an attribute, that's a function. So without passing anything to here, our random forest classifier, it instantiates the random forest classifier with the baseline parameters, aka this. And so that's what we want because we want to make some baseline predictions. So we go clf.fit, we're going to fit it on the training data as usual. And then we're going to make predictions. So ypreds equals clf.predict. No, we're going to predict on the validation data because we come back here. We want to tune our model on the validation split. So that's what we're basing our metric on, is we'll first create a baseline metric, which is by running our evaluation function on the validation split. Then we'll adjust the hyperparameters and try our model again on the validation split and see how they compare. So let's go here. So make predictions. We'll call this baseline predictions. And then we'll go evaluate the classifier on validation set. So we'll go baseline metrics. And this is where our evaluation function will come in handy. Metrics equals evaluate preds y valid. So see how we passed it the y, the validation set, and y preds. And then we want to go baseline metrics. Oh, what have we got? Local variable, accuracy, reference before. Oh, this is what we've missed out on. This needs to be accuracy score. Let's run this again. It's done terrible. Now what is going on here? Accuracy 0.22. Have we done this correctly? Oh, there we go. That's why. We've used our original. See, that was like that. We need to use heart disease shuffled because otherwise our model was predicting the original labels rather than our shuffled labels. So that's all we missed out on there. There we go. Whew. So we're getting this warning here that the value of n estimators will change from 10 in version 0.20 to 100 in 0.22. So this is our baseline metrics now. What we've done is we've created a train, validation, and test split. We've instantiated a model just as we had done before. We've fit it on the training data here. And then we've evaluated the baseline parameters, baseline hyperparameters on the validation set and got these metrics. So if we were to try and improve our results, if we were to try and adjust a model's hyperparameters, these ones here on our random forest, by hand, because that's what this section is, tuning hyperparameters by hand. How would we do so? Let's take this warning as an example of changing a hyperparameter. Let's change, and again, if you're using Scikit-learn 0.22 or above, you won't get this warning, but since we're getting this warning, we're going to try and adjust our hyperparameters. We'll change n estimators, which is this one here. We'll change it from the baseline of 10 to 100 and see if we get a different score on the validation set. Create a random seed 42. What we're going to do is create a second classifier with different hyperparameters. Because remember, instantiating our random forest classifier up here, passing it nothing, instantiates the classifier with the baseline hyperparameters it comes with right out of the box. So like using your oven's predefined settings when it comes out of the box to cook your favorite dish. These scores aren't really helping us out here. We want a better model. We'll create CLF2 and we're going to adjust the hyperparameters like you would adjust your oven to try and improve that favorite delicious roast chicken dish that you're making. Maybe you're preparing for a big function that all your friends are coming over and you've promised them a great dish, so you're trying to perfect it. That's what we're doing with our machine learning model. So again, same thing. Same data, fitted on the training data, but this time we've got CLF2, which is using n estimators as 100 rather than 10. And now, again, we could try different settings for all of these features here, the ones that we're going to try and adjust. But we might start with just one, see an example of it. And then we'll go make predictions. So y preds 2, because we're using CLF2, CLF2.predict x valid. We're doing the same thing as up here. The baseline predictions are on the validation set. And now make predictions with different hyperparameters on the same data. So different model, same data. And now we're going to evaluate the second classifier. CLF2 metrics equals, we're using our evaluation function again already, the one we created before. And we're saving a fair few lines of code by just calling it like that. All right. Now let's check it out. Ah, okay. So now if we compare Using the baseline hyperparameters that our model came with, what can we see that's different here? All we've changed is n estimators equals 100. So we've adjusted one dial on our model. So like adjusting one dial on your oven. We can see a slight boost in accuracy on the same data. So CLF2 has a slightly higher accuracy. It's got a higher precision, but a lower recall, and at the same F1 score. Okay. That's giving us a little inkling that maybe if we kept going with different hyperparameters, we kept trying to adjust them by hand, we would eventually just hopefully keep improving these metrics. So what would you think we would do next? If we go up here, maybe we try to change the max depth. So what's the default max depth? We find it in here. Max depth is none. So maybe we'd look at the documentation and go to the different variables that max length can take. So it can take integers or none. Default is none. The maximum depth of the tree. And doing our research, reading the documentation, we see some different values for max depth. So then we'd go back to our model here, and maybe we create CLF3 equals random forest classifier. This time we'll keep n estimators as the same, equals 100. And then we'll change max depth from none to equal 10. Now, I haven't made this number up. I've done some research, read the documentation, and figured out different ideas for max depth. And then we might do the same thing as what we've done here, evaluate our third classifier. As you might have guessed, or as you might have thought, if we're going through and adjusting all of these by hand, adjusting all the knobs by hand, that's going to take a fair bit of work, right? So just like perfecting your dish in real life, like if you're making favorite chicken dish, everyone's coming over for dinner, you're trying to adjust the settings on your oven, you may have to go through a bit of trial and error, right? You might cook it once and then it's not that good, and then by the 10th time you're starting to get really good. But that could take a lot longer with what we're trying to do here, writing code. If we have all these different settings up here, trying to change these, trying to find the best settings, that could take far longer than what we have. And the rule is, in code, don't repeat yourself. So you might have guessed, Scikit-learn has a way, a method inbuilt that can do this for us, try a bunch of different settings for us. And that's randomized search CV. But we're going to have a look at that in the next video. This one's already getting far too long. But the main takeaway here is that when we're tuning a model's hyperparameters, you can think of the training set as like the course materials where you're learning the foundation data. That's the training set. And then on the practice exam, you're refining what you know. So you've already learned all the baseline patterns like our model. And then with the validation set, we're adjusting the settings. So we're refining what the model knows, how it learns different things, before we test ourselves on the final exam. So in AKA, before we evaluate our model on the test set. Now don't worry if you're feeling a little bit overwhelmed, go back through the code that we've written, check it out. You could try out adjusting a few different hyperparameters yourself, but if not to worry. We're going to see in the next video how we can use a module in Scikit-learn to try different hyperparameters for us.